Alright gang, here we go. This is for Chem 2 Unit 11, talking about solubility equilibria. Okay, so it's time to remove another sneezing tree from your life. Several units ago I told you that there were certain compounds that were soluble and certain compounds that were insoluble. The fact of the matter is that even if something is insoluble, some of it will still break down and form ions in solution. Okay, but it just won't break down all the way. All right, so like silver chloride is insoluble in water, but in truth, some of it does break down and form silver ions and chloride ions in water. Okay, and so notice that because it only dissociates a little bit, we use equilibrium arrows. All right, and so this just brings us into another application of our knowledge of equilibrium. All right, and so the equilibrium constant that's associated with this experience is called the KSP, or the solubility product constant. Okay. So whenever we look at this, just one thing to remember, this guy is always solid, and these guys are always aqueous. So when we write out that equilibrium constant, the solid portion never gets written. So a couple examples of our equilibrium, or our solubility product expression. Barium sulfate is insoluble in water, but it still breaks down into barium and sulfate a little bit. Okay, and so our KSP expression would just be equal to that. Pretty easy. Barium phosphate here. Okay, notice that we've got a 3 here and a 2 here, so it's going to break up into 3 barium ions and 2 phosphate ions, so it becomes barium ion cubed and phosphate ion squared. Right, pretty easy, pretty easy. Now, one thing that gets students a little bit thrown off is thinking about these two ideas. We've got solubility versus the solubility product. They both have the word solubility in them, but they mean slightly different things. The solubility product is what you get when you take these ions to their coefficients and multiply them together. That's your solubility product. The solubility is defined as the quantity of a substance that dissolves to form that saturated solution. All right, so the solubility is an actual measurement of the quantity that's been dissolved. Okay, two common units for solubility is grams per meters and moles per liter. So just try to keep them straight. Okay, that's the big trick here. So solubility is a quantity that's been dissolved. Solubility product is that K value, or equilibrium constant. Okay, here's a little stepwise thing to help you go from solubility to KSP. All right, so if you're starting with solubility, okay, or mass of solubility, so this would be grams per liter, you'd use the formula weight to get it to molar solubility. Okay, and then you could go use your empirical formula to get it to molar concentration of ions. So this would be the whole of the compound, and then you can convert that using your empirical formula to get it into the concentration of the ions, and then from there you can plug those values into your equilibrium expression to get your KSP. You'd also go backwards to use your KSP. That would tell you exactly what two things multiplied to get your molar concentration of your ions. Then you can go to moles per liter if you needed, and then to grams per liter pretty simply. All right, so we're going to walk through a couple examples here. So we got the KSP for calcium fluoride is 3.9 times 10 to the minus 11th at 25 degrees Celsius. All right, and we want to find the molar solubility. So we're going from this KSP value to the molar solubility. So we're going from here down to this guy down here. Okay, so first thing we need to know is we need to figure out the molar solubility of the ions. So we need first this reaction. Okay, so we write out the reaction. You're always going to put the solid on the left and then the ions on the right. Just for a note's sake here, is if you took this guy, wrote it backwards, all right, so this would be Ca2 plus 2F minus, and you wrote it like this, so it forms CaF2. S, right, these would be aqueous, then this equilibrium expression would look like this. It would be K equals 1 over the concentration of Ca2 plus times F minus squared, right? And we call this one, because it's the opposite of the, or it's the inverse of the KSP, we call that the KF for the formation, okay, because it's two ions combining to form our solid. All right, so that's called the KF. So if you see KF written somewhere in your textbook problems or worksheet problems, that's what we're talking about. Okay, so anyway, so KSP is equal to this. So we got this guy here, and this guy is equal to that. Okay, now all we have to do is figure out, well, what would these two things be if they multiply together to form this? Well, in order to do that, we got to form our ice table. Okay, so we've got our initial concentration of calcium and fluorine are both 0. Okay, this guy doesn't matter because he doesn't participate in equilibrium because he's solid. Okay, so this guy's going to go up by x, and this guy's going to go up by 2x, because remember, our formula, or our equation, was CaF2 is going to form Ca2 plus plus 2f minus, right? So we're going to go up by 2x, so x times 2x. Plug these guys into our equilibrium expression, x times 2x squared, which becomes 4x cubed. Divide by 4, find the cubed root, and our x value becomes this, 2.1 times 10 to the minus 4th molar. Okay, and so if we wanted to turn that into grams per liter, so this is the molar solubility, but say they wanted the mass solubility, all you'd have to do is multiply by the molar mass, okay, of that calcium fluoride, and they say you'd get 0.016. You can try that on your own. All right. Factors that affect solubility. So this is just another application of our common ion effect. Several videos ago we talked about the common ion effect, and this is essentially the same thing. Specifically before we talked about the common ion's effect on pH. All right, now we're talking about it on its effect on solubility. So if you have two things that are mixed together and one of the ions in the solution in equilibrium has already been dissolved, then the solubility of that salt will decrease. All right, so for example, we have CaF2 and it's being dissolved in a solution of sodium fluoride, right? CaF2 becomes, we just wrote this out, but we'll write it out again just for funsies. So Ca2 plus 2F minus, right? And then the NaF will become like this. NaF, will become Na plus F minus. Okay, and so in solution we already had this guy here. Now because we had this in solution and we try to put in calcium fluoride, it would increase the concentration of this fluoride ion, therefore increasing the reverse reaction, so we'd shift, so we'd be able to dissolve less of our solid. So in pure water right here, where there's 0 sodium fluoride to start, our calcium fluoride is the value that we calculated right here, 2.1 times 10 to the minus 4th. Okay, but as we start increasing that concentration of sodium fluoride, so here they had it at 0.05. Notice how when the sodium fluoride concentration is still pretty dang low, it's going to form this. Now remember, so one thing here that you should keep track of, sodium fluoride is completely soluble because of that sodium ion. So really that's not an equilibrium, that forms all the way. All right, so that completely forms this guy. All right. So anyway, so as you increase that fluoride ion concentration that's in solution, your calcium fluoride becomes less and less soluble. So how would we calculate the solubility when there's a common ion? Well, essentially it's the exact same thing. So in this example, we're starting with calcium fluoride again. Okay, but now it's in a 0.01 molar solution of calcium nitrate. So our common ion is this calcium. Okay, so now we got to keep track of that calcium. What has it done to our solution? Our expression and our equilibrium expression are the exact same thing, right? It's the CaF2, Ca2 plus 2F minus, and then our KSP is still equal to that value there. Remember, this KSP only changes if we change temperature. So now we set up our ice table, and everything looks exactly the same except for this guy right here. Now, at the initial, this is our concentration of calcium. Right, because we've had this already in solution. So our calcium did not start at 0. It's got an initial concentration. All right, but we still go up by x and up by 2x, so it becomes this guy here. Now, so this becomes, so we can plug all that into our KSP expression. It becomes this guy here, right? And we get this 0.01 plus x times 2x quantity squared. All right, but remember that this value here is 1 times 10 to the minus 2nd or so, and this is times 10 to the minus 11th. That's like 9 different, so we can neglect that x. So essentially, this just becomes this. Okay, so you divide by 0.01, divide by 4, and then take the square root, and you get an x value of that. And then notice before, remember our x value was when there was no calcium present, it was 2.1 times 10 to the minus 4th. And now it's 3.1 times 10 to the minus 5th. So it's 10 times less soluble, even when you only have that 0.01 molar calcium fluoride, or calcium nitrate was in there before. It's calcium nitrate, right? Yep. Okay. pH can also affect your solubility, and in order to understand how to do that, you have to remember your rules for finding out whether or not a salt is acidic or basic. Okay, so if the substance has a basic anion, it will be more soluble in an acidic solution. Okay, so remember your buffers control pH. So when a buffer is used, there would be no change in the concentration of hydroxide ion. So let's see what this would look like here. So if you have, this is lead fluoride. It's insoluble in water, but some of it still dissolves, right? And so lead fluoride would look something like this. We'd have PbF F2 is in equilibrium with Pb2 plus 2F minus. And this makes sense, right? We've got 1 lead and 2 fluorines floating out in solution. Now, if we stick this in a hydrofluoric or in some acidic solution, so we've added H plus to our solution. Well, we know F minus is weakly basic, so that means this F minus that's in solution will go ahead and form hydrofluoric acid. Okay, and so what occurs here is this now, because this is reacting, this F minus, this concentration is going to drop. So now we're going to increase the amount of this that can dissolve. Okay, so as this occurs, we have more and more of this PbF2 that can dissolve in solution, and the F2 gets turned into the HF. All right, so and we can see this down here. There's lots of PbF2 solid, and then here there's only a little bit left. All right. But if we have something slightly different, look at like we have lead iodide, right? So Pbi2. Well, this is going to dissolve to form Pb2 plus 2I minus. Okay. Now 2I minus, right? I minus is from a strong acid, so it is a negligible base. I minus is negligible. Negligible base. All right, so because it's a negligible base, it will not steal hydrogens, right? So it cannot react with the protons that are in solution. So now we just have these hydrogens floating around, and notice that the solubility of our lead iodide did not change. All right, let's do a couple practice problems. It says, which of these expressions correctly expresses the solubility product constant for Ag3PO4 in water? Well, this is pretty easy. What we got to do is write out our equilibrium expression for Ag3PO4. So this guy becomes that. So we're going to get 3 silvers and 1 phosphate, 3 minus. So our KSP is going to be equal to Ag plus cubed times PO4 3 minus. All right, so does that match one of our guys here? Let's hope so. Ag cubed plus, nice. Boom, nailed it. Now it says calculate KSP from solubility. It says you add 10 grams of solid copper phosphate to a beaker and then add 100 milliliters of water to the beaker at 298 Kelvin. The solid does not appear to dissolve. You wait a long time with occasional stirring, eventually measure the equilibrium concentration of copper in the water to be this. What is the KSP? All right, so let's think about this. So we want to find the KSP. So copper 3 phosphate. So essentially what they're saying is this sucker's insoluble. This 10 grams is just telling you that they put a lot in this solution. Okay, we're not going to have to use that value. So this becomes, well, phosphate is 3 minus. So that means it was a Cu2 plus, and we're going to get 3 of those guys. All right, plus, oh, I guess I could have seen the 2 plus right there. Would have clued me in. And then we're going to get 2 phosphates. All right, so that's our expression here. So our KSP. Okay, well, our KSP is going to be equal to Cu 2 plus cubed times phosphate 3 minus squared. Okay, and we want to find the KSP. So that what we need in order to solve for the KSP is we need values to plug in. Well, we have the concentration of copper. That's easy. Concentration of copper is just this one right here. Now we need to figure out the concentration of the phosphate. So what we could do is we can use this formula here to just convert moles of copper into moles of phosphate, right? And it's in 100 milliliters, but, you know, and what we could, you know, the absolute proper way to do this is multiply this by 100 milliliters, and then once we get it back into the concentration, divide it by 100 milliliters. But we know that 100 milliliters is going to cancel. So really we just need to find out, we can use this value because they're in the same solution. We can use that value straight up to go from moles to moles. Okay, so we get 5.01 times 10 to the minus 8th, and this is moles of copper 2 plus. All right, we're just going to use a little bit of stoichiometry, and so balanced chemical equation for every 3 moles copper, there's 2 plus. There's 2 moles of phosphate, PO4 3 minus. Okay. So 5.01 e to the minus 8th times 2 divided by 3. And so you get 3.34 times 10 to the minus 8th. All right. So just slightly less than what the one was before. Now this is the molarity of the phosphate. Okay, so now we got the molarity of the copper and the molarity of the phosphate, so now we can plug everything into our KSP. So the copper value was what they gave us, that's the 5.01 times 10 to the minus 8. All right, and that guy's cubed, and then the phosphate was the 3.34 times 10 to the minus 8th. All right, and that guy is squared. All right, so we say 5.01 e to the minus 8 to the third times 3.34 e to the minus 8, and we'll square that. Okay, and I got 1.40 times 10 to the minus 37th. 0 times 10 to the minus 37th. And so there's your answer right there. Bam. Bob's your uncle. Anyway, so that's that one. And then last one here, it says predict the effect of acid on solubility. Okay, so which of these substances are more soluble in acidic solution than in basic solution? Okay, so we're going to walk through their logic for each of these guys here. All right, so what we really want to do is look at the anions here. Okay, all right, and decide whether or not the anion is basic. Okay, so sodium hydroxide. So the anion here is OH minus. OH minus is a strong base. Okay, so it's going to act like a base very, very easily. So when you put it in acid, that acid, right, if you put it in acid here, that hydroxide that you had from this guy is going to react with the acid and water, forming water. So it's going to pull from this side. Le Chatelier's principle means it's going to shift this way. So it's going to be more soluble in acidic solution. Calcium carbonate here, the calcium carbonate, well, the anion is this CO3 2 minus. That is also a weak base, so that thing's going to react with the water or the acid in the same way. It's going to form this guy, and it's going to eventually form your carbonic acid. Okay, and because of that, it's going to pull away from the carbonate, which is going to form this guy, so it's going to be more soluble in acidic solutions. And they've walked you through how they come up with this whole overall equation. It's pretty simple, though. We take this calcium, all the things that we've just talked about, add them up, and we get all of these guys here. Okay. Solubility of BAF2, okay, is enhanced by lowering the pH because F minus is a basic ion, right? So again, F minus here is a weak base, so it'll react with the acid that's in solution, forming your HF. All right, and so our overall equation looks like this. Okay, so the solubility is enhanced by lowering the pH. So essentially, if our anion is basic, our solubility increases in acidic solution. Now AgCl, the anion formed here is chloride, and this is the anion of a strong acid, so it has negligible basicity, so it won't react with the acid that we have in solution. So therefore, silver chloride is a its solubility is not affected by having an acidic or a basic solution. So that's it for this video here. Make sure you do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.